Words and then, yeah. So, ladies and gentlemen, this begins a series of 4 lectures now by Jack Tuszynski on quantum biology. He hasn't taught in the course for about 2 years, year and a half. And so it's exciting to have him back. And if you think about like what parts of the course are most cutting edge, I would really think that it's this part, that everything else we've taught you thus far, can find other courses that are teaching it, but most courses about the future do not teach about quantum biology. So I'm very proud of this part of the course, and it's been one of our most popular features. So, Jack, I think you can take it away. Okay, welcome.
Yeah. Great to be back. Thank you very much for the kind introduction, Kim. I hope you're seeing the slide deck. I'm going to go into the presentation mode. All right, so yes, it was a long break, and during that time, a lot of things happened. COVID, first and foremost, and also this explosion of information technology applied to things like virtual classrooms. This is one of them, and I'm getting used to it now. Before I start with this topic, this will, as you said, will be 4 lectures. They are divided into themes, and I presume that this audience is largely non-physics based. Yes. So the first lecture will be kind of introduction, because we cannot really talk about quantum biology without talking about quantum physics, but it'll be a gentle introduction to the topic. The second lecture will be sort of quantum biology proper, what we currently know about it. The third one will be more on the neuroscience toward consciousness. I think quite intriguing to all of us. It's just kind of under the theme, all you ever wanted to know about consciousness, but were afraid to ask, because this is one of those topics which scientists are very shy about. And finally, there will be some other, in the 4th installment, some more exotic topics, I think, which I think relates to quantum phenomena in not only biology, but also psychology or psychiatry. I've been involved in some small communities of people who are interested in applications of quantum physics or quantum physics concepts across various fields. Maybe I'll even find time for quantum finance, which is actually possibly lucrative. We'll see. I want to say a couple words about myself. I'm trained as a physicist, and if you see these symbols, physics oncology, between the brackets, pointed brackets, this is actually a quantum mechanical symbol introduced by Paul Dirac, Bra, and Ket. It's a technical terminology, and this indicates that I kind of started in physics, transitioned to oncology, spent 15 years in the Department of Oncology, doing computational drug discovery mainly. And then a year ago, I transitioned back into physics. So I'm kind of oscillating, and right now in a superposition state, mainly in physics, but also doing oncology. So it's very appropriate.
Yeah. Excellent.
So the title is 100 Years from Quantum Physics to Quantum Biology. Actually, it's 121 years from quantum physics. Quantum biology sort of erupted on the scene about 15 years ago or so, maybe less. And the question is, how long to quantum medicine? Because of course, from biology to medicine is not that far away. But first of all, we need to understand the concepts. So first, some shameless plug on some of the publications I made in this field and the areas around it. And nano-neuroscience, published with my colleagues Nancy Wolf from UCLA and Avner Priel from Bar-Ilan University in Israel. And then this book in the middle, The Emerging Physics of Consciousness, is a collection of chapters from different authors, has been kind of popular in this field, and then Biophysics of Consciousness with two other collaborators, Roman Poznansky and Todd Feinberg. So this is roughly the outline. As I said, there may be some surprises down the road, but I will start with the discussion about the world before quantum physics, what we call classical physics. So classical music and modern music. I think we have classical physics and quantum physics. Then, so this will be today, as well as quantum physics on a sort of pedestrian level. So you don't need any mathematical basis. There'll be a few equations, but really we won't be solving any of the equations or problems. And then we'll, next week, we'll talk about quantum chemistry and quantum physiology, which by this I mean really metabolism. And of course, quantum biology. There are not that many cases which we can call quantum biology, which are experimentally validated, but the list is growing. And this is not too dissimilar to what physics went through at the turn of 19th and 20th centuries. So the fact that there are a few cases only that look like quantum phenomena play a role in biology doesn't mean that it's not a widespread phenomenon. Then a little bit of quantum computing, which is now all the rage, and why not? And then quantum brain or neuroscience and quantum anesthesiology. I'm currently involved in a very intriguing and interesting project funded by the Templeton Foundation. Perhaps next week I'll say a few words about what we are trying to demonstrate in regard to anesthetics. There's a few hypotheses, and we try to experimentally determine that anesthesiology or anesthetics actually work on quantum principles. So I think we are moving from sort of hypothetical to more experimentally based. And then finally, time permitting, I want to say a few things about quantum psychology or even psychiatry. I've had some interactions with people in these fields who are surprisingly to me very open-minded to physics ideas, which are slowly penetrating into this world. And I hope you'll appreciate that this is sort of forward-looking, very futuristic in a way, because there is very little solid experimental background, but there is a lot of evidence or suggestions that phenomena such as those in quantum physics, or concepts rather than phenomena, make sense within the context of human psychology. So let's start with some historical. I mean, most of today's lectures will be historical, and this is the beginning of this story. So the end of 19th century, in fact, 1894, Albert Michelson, who got a Nobel Prize for measuring the speed of light, stated in a address to the Royal Society, I believe, which is attributed incorrectly quite often to Lord Kelvin, but that was Albert Michelson. He said that it seems probable that most of the grand underlying principles have been firmly established. The future truths of physical science are to be looked in the 6th decimal place. In other words, he thought that physics was done and the rest was engineering and maybe fine-tuning of some of these measurements, but nothing really to be discovered was left. In fact, there is a book I think published perhaps 15 years ago called what remains to be discovered. And there's a list of things to be discovered, but this is a very dangerous game because discoveries are by definition unpredictable. So if you want to write a book about what's to be discovered, then you already kind of came up with a conclusion that that nothing is to be discovered, or nothing of importance. So this was the status quo. Actual physics until that time, which is over the past previous 2.5 centuries, I believe, or 3 centuries, have been making incredible advances in our understanding of the world, material world, starting with Galileo, of course, and then classical mechanics was developed by Sir Isaac Newton and Lagrange and Hamilton. Very elegant, very powerful, and of course it allowed us to construct buildings and build machines. And then that led to the later on to the discoveries of electromagnetic phenomena by Ampere, Faraday, others, and culminated with Maxwell's theory of electromagnetism and Maxwell's equations, which serve us very well even today with the electromagnetic means of communication, including those that we use right now. So this is all 19th century. And then the Industrial Revolution called for the developments of machines and engines, and that required the study of thermodynamics, transformation of heat. And these are the names of the major builders of this field. Gibbs, who was actually the really first-rate American physicist. Until then, most of the developments in physics took place in Europe, in England, France, Germany, Italy. And then we have Carnot, Thomson, Clausius. Following that, there was a deeper look into what really heat represents, and molecular nature of matter became the focus of our investigations. And that led to a field called statistical mechanics, not to be confused with statistics because it's quite different. Statistics is a branch of mathematics. Statistical mechanics is the field developed by Nernst, Helmholtz, and especially Stefan Boltzmann, who linked probabilities and energies, and so energetic states were involved in the definition of probabilities of occurring of these states. So this was basically the physics, the building blocks of physics before quantum mechanics. Very nice, very neat, very elegant, very mathematically precise and beautiful, in fact. And there were basically two kind of approaches, two independent approaches to physical phenomena. Waves, such as sound waves or ocean waves, even radio waves, were understood as propagating disturbances, periodic disturbances going up and down, and defining the amplitude, propagating through space, having a defined wavelength and the frequency, as well as velocity. So this was one type of approach to studying various physical phenomena. It was either wave or a particle or material object, such as a ball. And I guess most of you, when you take physics 101 or 124 or something like this, get bombarded with these kinds of examples of falling flower plants from the balcony as examples of objects under gravity, and kind of boring, but nonetheless important to understand the phenomena. So these objects have masses and well-defined positions, X, Y, Z, in Cartesian space at a point in time t, and move with velocity v, and could sometimes be experiencing acceleration a. So very neat, very elegant, but with limitations. So particles and waves in this sort of classical world of physics do not meet in a way. The two solitudes that never twine, two extreme visions of reality. Particles collide, or even break into pieces, or get shattered in collisions. And waves can propagate in space and can interfere, superimpose each other, and in contrast to particles, waves are extended in space, particles are localized in space and cannot pass through each other. So these are the two opposite sets of phenomena or objects in classical physics. So in one word, the classical world is deterministic, which was very aptly put by Simon de Laplace, one of the founders of mathematics of the time and physics as well. He said that if we were able to determine the positions, velocities of all physical objects at the time and space, at a particular time, we could completely predict the future of the universe using Newton's laws of motion. So that was a very bombastic statement, which today we know doesn't hold water, not only because of quantum mechanics that we will discuss in the next hour or so, but also because of nonlinearities and things like chaotic phenomena, which are not quantum. In the classical world, they're also not predictable, unpredictable situations. But this is the departure point for quantum mechanics, because the quantum world is probabilistic, is not deterministic, is unpredictable. The only thing we can do is predict probabilities or evolution of the possibilities, if you will. Furthermore, I mean, we'll get deeper, but there are some very fundamental philosophical differences between the way we see the world through the classical lens as opposed to the quantum lens. Okay, so there's here the observer and the observed. In the classical world, the observer is supposed to be benign and does not interfere with the object that is being observed, and does not change anything. So we can classically claim to be providing objective information about this state of the object that we study. In quantum mechanics, such a thing does not exist. Every observation that you make about the object, quantum object, affects it, because even the tiniest disturbance, such as a single photon, a single ray of light, will change or disturb the position and the velocity of even the smallest of the particles. So this was a incredibly profound, and we still grapple with this concept, but it was an incredibly profound departure from the way we viewed the world then and we view it now. I think most of us still view it in the classical sense because our intuition, our sense of reality is grounded in this classical picture that we are just observers looking around and seeing the world as it is. In fact, quantum phenomena are completely counterintuitive, and I don't know anybody who can sort of think about it as a natural way of viewing the world. But let's go back to the chronology of quantum physics, and here's the first 4 decades of it, starting with 1900. Appropriately, I think it ushered into the 20th century with a big bang. Max Planck introduced energy quantization to explain the radiation, black-body radiation spectrum. 1905 is a very important year for Albert Einstein, who not only explained the photoelectric effect, but also wrote a revolutionary paper on the special theory of relativity. And paradoxically, Einstein got the Nobel Prize for the photoelectric effect, which is kind of incidental. It was a building block toward quantum mechanics, but it was not the most important contribution that Einstein made to physics. And definitely special and general theories of relativity were much more important. And in fact, Einstein never truly believed in quantum mechanics even until he died. But nonetheless, he got the Nobel Prize for it. Then 1913 was also a very important year. Niels Bohr in Copenhagen explained the atomic spectra and atomic energy levels. Louis de Broglie in 1924 introduced the wave-particle duality. So this is the connection to what I was saying a few minutes ago about waves and particles in classical physics, in the classical world. Louis de Broglie actually showed that in the quantum world, particles such as electrons and protons can be seen equally well as waves or as particles. And in fact, that distinction in quantum mechanics doesn't exist. Every object is a quantum wave, and sometimes it can manifest itself as a sort of particle, but it's almost like an obsolete way of thinking about the world. And then in 1925, shortly thereafter, Werner Heisenberg and Erwin Schrodinger developed very powerful mathematical formulations of quantum physics. Heisenberg used the operator formulation and Schrodinger the wave function equations. And then 2 years later, Werner Heisenberg also formulated something which is again a complete departure from our intuitive perception of the world, namely the uncertainty principle. And the uncertainty principle states that, and we'll come to it later, but basically you cannot, even for a single object, single quantum mechanical object, you can never obtain complete information about this object. You cannot have the knowledge of position and velocity, or we call it momentum actually, in physics, or energy and time at the same time. So it's impossible by the sheer structure of quantum mechanics to have complete knowledge about any object, not the universe, like Laplace said, but even the smallest object in the universe. And then 1927, Paul Dirac in England unified quantum mechanics with Einstein's special relativity. So he actually created relativistic quantum mechanics. And then 32, John von Neumann provided a rigorous mathematical formulation of quantum theory. And John von Neumann is also known as the father of modern computing, computer science, developed principles for computers. And then we kind of stopped this timeline in the 1940s, although the development of the theory continued, but it became quite intricate, so we don't need to go deeper. Richard Feynman, Schwinger and Tomonaga introduced quantum electrodynamics. And this is the beginning of a very mature stage of quantum theory called quantum field theory. So instead of particles and waves, we now have quantum fields. I will not be able to spend any time on this construct because it's quite mathematical, and we don't really need to know it for the time being in connection with biology, especially. But suffice it to say that until that moment, actually, quantum mechanics was called wave mechanics, and so quantum field theory is a very elegant, advanced approach to it. Let me very quickly go through some momentous events on this path. So actual radioactivity was discovered in 1898 by Marie Curie. And that was actually an example of a quantum phenomenon because it showed that elements can transmute and emit radiation, which is a quantum process classically could not occur. J.J. Thomson discovered the electron as a fundamental particle of nature and actually responsible for electric currents. Until that point, we didn't know what was actually the carrier of current. And I mentioned Max Planck. This is maybe worth spending a moment of our time trying to understand what actually Max Planck did, and we'll come back to it actually on Tuesday, because there is something quite analogous in biology to this problem of quantization. So what Max Planck, against his own intuition, proposed in order to explain the intensity profiles of radiation emitted from so-called black bodies or objects at a given temperature, in order to do it, he tried and used all the classical thermodynamics that was available at the time, and nothing worked until he proposed that energy of radiation comes in packets. Now we call them quanta, and each packet carries 1, 2, 3, 4, etc., but integer numbers of quanta, and each quantum of energy is equal to is proportional to the frequency with which radiation is oscillation frequency f, and then he introduced this little constant h, which was basically a fitting parameter. Like when you want to fit to a curve, experimental curve, you adjust it and turn the knob and find it. This constant, Planck's constant h, is equal to roughly 6.6 times 10 to the minus 34th, 10 to the minus 34th joule times second. You can look it up. It doesn't matter, but what matters is that the constant that was obtained empirically turned out to be a fundamental constant of matter. That is not something you can derive from anything else. It is simply given by a higher authority. This is how the universe works. Whoever gave us that constant knows what it means, but it's amazing that Planck just fitted experimental curves and obtained one of the most important physical constants we know today. And it popped up later on in different contexts. So it's not just one curve or two curves of the same type that you can fit to with this constant, but it's actually shown in many other phenomena. So kind of, I would say, serendipity combined with a great mathematical skill of Max Planck. He got a Nobel Prize in 1918 for it. And by the way, Max Planck was one of the more senior physicists at the time, and it helps actually if you have a full professorship in Göttingen or Heidelberg or Oxford to promote your ideas. So that two interesting things here actually. The first one is that most of the developments occurred within a very small geographic area. In Germany, some in Denmark and Switzerland, Austria. And the second is that a lot of young people took part in this revolution. And actually, Max Planck was one of the more advanced in age. I think he was 42 years old or something like that when he discovered this formula, and that was really old by that standard. I think Einstein was in his late 20s. So it's a sociological observation, and that's the formula that he proposed or derived in full glory. It's the intensity of radiation as a function of the wavelength lambda and the different temperature T. So it reflects a lot of known empirical facts of the time, Wien's law, and so on. And you here in this formula see in the denominator 1 over e to the power h c over lambda kt. H is the Planck constant, and you see here 6.6 times 10 to the minus 34th. Okay, so I'll stop it here, but remember the Planck constant. And you must have heard about the Max Planck Institutes. So in Germany, these are the premier research institutions. I don't know how many, but there are quite a few for not only for physics, but also for geology and biology and so on and so forth. So he left a huge legacy. Now, I mentioned de Broglie and so a lot of interesting characters. I think one should write a script for a Hollywood movie about the birth of quantum mechanics with Max Planck, Einstein, and others playing major roles. This guy, Louis de Broglie, he was a count, actually, an aristocratic member of the French nobility. And I believe he jumped right to a PhD thesis for which he got the Nobel Prize, bypassing all the intermediate steps in his scientific career. So that was a stroke of brilliance. And his prediction was that electrons behave like waves, and sure enough, J.P. Thomson also got a Nobel Prize with high energy electrons demonstrated interference patterns from objects. And this is an electron. You must have heard about the electron microscopy. It's a technique that is used for imaging in various structures, biological structures, proteins sometimes, or larger. And this is an electron microscope picture of a fly. So electrons here are used as waves that interfere with each other and show the patterns of constructive and destructive interference. Just like as X-rays also, well, the X-rays are electromagnetic waves, so we know that, and they form crystal. This is crystal images, not crystals. Electron diffraction patterns. The panel in the middle shows you different numbers of electrons interfering from 10 to 200 to 6,000, 40,000, 140,000 in the last one at the bottom. And what de Broglie actually demonstrated is the wavelength of the particle. And I said before that that's a misnomer, but nonetheless, for the sake of argument, let's say that the particle, like an electron or proton, is moving at the velocity v and has a mass m, then the corresponding wavelength is equal to the Planck constant divided by this product of mv, which is momentum. And this is a very simple looking formula, but has an incredibly profound meaning, linking particle-like behavior, that is momentum, mass times velocity. Particles have mass, waves don't have a mass, and linking it to the wavelength of a wave. So you see two seemingly incongruous properties captured by one formula. This is the photoelectric effect that Einstein explained. Basically, incident light on an emitter plate in a cathode, in a cathode, if has enough energy, and that means high enough frequency according to Planck formulation. Remember, energy is proportional to the frequency, to the Planck constant. If the frequency is high enough, that means energy is high enough, and this energy should be sufficient to release an electron from this emitter plate And if there's an electric field, this electron will be attracted to the opposite plate, the collector plate. So this is from the anode to the cathode, and that's how it works. So it shows that light is quantized in the form of what we call them photons. So you can assign a particle-like behavior to light, because light here strikes out an electron as if it was a golf ball hitting another golf ball, but it's actually a wave that is releasing a particle. But in this crazy quantum world, you cannot really call one a wave and the other a particle. Both are waves or both are particles, depending on how you look at it. I hope I'm not confusing you too much, but that's the nature of the beast. It's a little bit difficult at first to understand what's going on. And if the wavelength is too long, that means frequency is too low and energy too low, then the electron will not be released from the emitter plate, because there is something called the work function, that is the amount of energy needed to eject the electron, which is attracted to the nucleus of that metallic atoms in the plate. So that was Albert Einstein's Nobel Prize, basically on 2 slides. And this is the Rutherford's model of the atom, which Niels Bohr. Rutherford has some connection to Canada. He was a professor at McGill for a few years, came from New Zealand, and he, for the first time, experimentally revealed that the atoms have structure that is here represented a bit like a planet or solar planetary system, with the nucleus forming something like the sun, the center, and then the electrons orbiting around a bit like planets. But that's of course just a cartoonish representation of the actual situation in physics. Niels Bohr solved the equations for this model of the atom, hydrogen first and helium and others, and obtained the energy levels at different states. This somewhat simple or simplistic observation, and well, the calculation wasn't that simple, but that led to an immense number of applications. Everything that we can today recognize coming from distant stars can be identified because of this. This is the line spectra of atoms and eventually molecules. So the spectra correspond to transitions between states of electrons orbiting the nucleus in different atoms or molecules, and these transition rates or transition energies differ depending on whether it's rubidium or lithium or nickel, whatever atom you choose. The energies differ, and you can identify them by the color of the light that is either absorbed or emitted, and the absorption and emission has to do with transitions of electrons, which either use the energy to go to a higher orbit or come down and emit a light when they come down to a lower orbit. The lowest energy state is always called the ground state. And anyway, that's the birth of atomic and molecular spectroscopy, which has spawned numerous applications. We basically can identify molecules, even small impurities in various samples. We find composition of stars. We can analyze pigments in the paint, identify pollutants in the air, and monitor car exhausts, and so on and so forth. There is basically no end to spectral line analysis or spectroscopy. But let's move on to something which is, I think I mentioned earlier on, which is again counterintuitive within the classical mindset, I should say, and that is the what's called the Heisenberg uncertainty principle. So Werner Heisenberg demonstrated mathematically that within the construct of quantum mechanics, no object can simultaneously reveal its position and momentum, or position and velocity within complete precision. There's always a limit on the precision of our knowledge or about anything, any object, and that limit is called is on the right hand side, is actually the Planck constant again divided by 4 pi. So that's kind of depressing in a way, because it tells us that our knowledge about the universe is limited by definition. If within the quantum world, even a single particle cannot be completely known. And that applies not only to position and momentum, that applies also to other characteristics of these objects. I don't have that here, but for example, 2 components of the angular momentum, or energy and time, so-called conjugate variables. If 2 variables in quantum mechanics, which are like position and momentum, are called conjugate, you cannot know them both at the same time. Now, this is the biggie, Schrodinger. Schrodinger introduced something which is quite profound. And by the way, I wanted to say that every name I mentioned in today's talk is a Nobel Prize winner, and not a small one. These are the Nobel Prize winners that stay in the history books. I don't want to dismiss Nobel Prizes, but I kind of, well, last year Roger Penrose got a Nobel Prize in physics, and I will remember that name for a long time. But sometimes there are Nobel Prizes given to people that made huge contributions, but well, and that Aaron Schrodinger is one of those, but sometimes actually not that big of a deal. So Schrodinger's Nobel Prize is enormous. So he changed our in physics at least, fundamental approach to how we describe the reality by introducing the so-called wave function. So I told you in the very beginning about particles with position and velocities in Cartesian coordinates. So Schrodinger basically said that there is no such thing, because it would define the limits of a particle, like a golf ball, a ping pong ball, or soccer ball. That's your particle. No, it's not like that. You have to think about it more like a cloud, which is deformable, and this extent of the particle is given by this wave function psi of x and t, or position and time. It evolves, it changes. So particles are a bit like, wave functions are a bit like clouds representing particles, and sometimes they actually superimpose with other wave functions and so on. So this is the beginning of a completely new description of reality. There were some other experiments. I'm not going to linger on that. So the empirical basis for quantum physics kept growing, including something called the spin. I'll come back to it in a minute. And so this is quantum theory in essence. Quantum systems or physical systems exist in discrete states, but can be in any number of states at the same time, which is again a bizarre world where a system can be in 2 states at the same time. You know, you must have heard about the famous Schrodinger cat, which is both dead and alive in a suspended animation, or called a superposition state. So quantum particles literally exist in such superposition states. So we only introduce probabilities instead of certainty of knowing where things are. And there's a few quotes here about this. Einstein didn't like this idea of probability in physics. He said God does not play dice, because that's what probabilities are all about. But Richard Feynman, one of the most colorful physicists of 20th century and geniuses, also a Nobel Prize winner. I mentioned everybody here that I mentioned got a Nobel Prize. Said that things on a small scale behave nothing like things on a large scale. I hope you can accept nature as she is. Absurd. Okay, so that's one way of looking at it. And then Niels Bohr said that anyone who is not shocked by quantum theory has not fully understood it. Let's see, why am I not able to? 1 second. Okay. So here is a very famous photograph. There was a few conferences at the time organized in Brussels, so-called Solvay conferences. Solvay is a chemical company still in existence, I believe, which sponsored these conferences, and these conferences basically solidified the development of this field and formalizing it. And here you see some very famous people. On the left, you have Max Planck with the mustache and the hat in his hands, and next to him is Marie Curie, and there's Jordan, and there's Albert Einstein, and there's well, I can't recognize everybody, but I see Schrodinger just 2 heads above Einstein, and Dirac to the left of him, just above, and so on. There's a lot of Nobel Prize winner. Maybe everybody here is a Nobel Prize winner. I wouldn't be surprised. Oh, Debye as well. So, okay. So Wolfgang Pauli introduced something even more exotic, because so far we've been sort of associating things that are at least intuitively understandable, such as wave function, so it's a cloud, all right. You have momentum, which is mass times velocity or something like that. But Pauli introduced something which simply is not intuitively understandable. It's called spin. So there's basically a quantum variable that doesn't exist at all in the classical world. Electrons have spin 1/2, and spin can be either up or down. That, by the way, is the necessary ingredient of magnetism. A kind of bizarre thing, because magnetism, everybody played with magnets. You can buy a magnet, a very strong neodymium magnet, for $5 in the dollar store, or maybe $2 even, I don't know. And this is an example of a quantum phenomenon, because the magnet is working the way it is because of the alignment of spins in one direction and creating a very strong magnetic field. So he introduced it for completeness, and actually this also explains the periodic table of elements. Without spin, you cannot explain all the numbers of electrons in different orbits for various atoms, and therefore there would be no explanation of why you have those elements the way they are ordered originally by Mendeleev. And then on top of that, in the quantum world, there are 2 types of particles, or objects, if you will. Fermions, after Italian physicist Fermi, are half-integer spin particles, and bosons, after Indian physicist Bose, are integer spins. So half-integer means 1/2, 3/2, 5/2. Bosons 1, 0, 1, 2, 3, 4, and they have completely different properties. Okay, I will come back to it a little bit, but this may be taking us on a tangent that it's interesting, but not necessarily, perhaps not necessary for quantum biology, although maybe it is. Come to think about it. In the second lecture, probably next week on Tuesday, we'll talk about magnetoreception, navigation by birds, basically, such as European robins and the birds which migratory birds. And to explain their inner compass, you need this concept of spin. So things find their strange ways into biology from physics. So the basics of quantum mechanics are such that by and large, we tend to agree that quantum mechanics is needed to explain microscopic phenomena. Classical physics works well in microscopic domain, but there are also microscopic quantum effects. So it's not quite sharp to divide it this way, because superfluids, superconductors, lasers, and even crystals, dynamics of crystals can only be understood by quantum mechanics, and I mentioned magnets. Okay, quantum mechanics was developed by postulates, which I'll go through in a minute or two, and that these postulates were a result of these Solvay conferences. You saw the Nobel Prize winner sitting there pretty in front of the hotel in Brussels. This hotel, actually, I visited. I spent a year in Brussels, and I couldn't resist to see this historical place for me as a physicist. It's called Hotel Metropole. It used to be a bit like Hotel MacDonald in Edmonton, a kind of a very elegant, opulent place. And when I went there, it was a bit shabby, but I still got the goosebumps to be in the place that those people were debating the origin of quantum theory. So the basis of quantum mechanics is the wave-particle duality. I'll just highlight the main differences: probability, language of probabilities, the observer problem, because you cannot understand any physical system at this level without observing it somehow or measuring, and every act of measurement it disturbs that system, perturbs it, and changes it. And then quantization, that's the word that is most directly associated with quantum mechanics because of the energy quanta, or integer units of energy. Okay, let's now go through the postulates of quantum mechanics. There are 4 of them, which were formulated in the 1920s. So the first postulate is actually what Schrodinger introduced, the wave function of the state function. Every system has a state function that describes its state, so, and what's also important is that the state could be a superposition, a sum of 2 wave functions. So a particle could be 2 energy states at the same time, or could have spin up or down at the same time. The second postulate is actually linking this wave function to probability. The square of the wave function is a complex number, so you have to take the absolute value, square it, and it gives you the probability of being at a given point at a given state. The third is really mathematical, and that is how you build the description, mathematical description of physical systems in the quantum representation, namely what we in classical physics would describe as properties of systems. For example, a property would be a position, location, if you will, momentum, which is proportional to velocity, or energy. All of these properties, which are so neat and tidy in classical physics, become Hermitian operators. So this is a technical term meaning that these are differential operators acting on functions with specific properties. And I will not go beyond that because that requires a bit of advanced mathematics. But you have here examples of these operators. Position is simply multiplying the wave function by x. Momentum is a differential operator differentiating with respect to x. Energy is also called the Hamiltonian operator, which is has the kinetic energy. You must have heard about kinetic energy in classical physics. Is 1/2 mass times velocity squared, but in quantum physics, it's a second derivative with respect to position multiplied by a bunch of constants, including the Planck constant. And then there you have the potential. And the last one, the fourth postulate, is kind of interesting. It's really what Newton's equations are to classical physics. This is the Schrodinger equation, which describes the evolution of the wave function in quantum physics. And so this was not derived because it cannot be derived, but it was postulated by Erwin Schrödinger in 1926. There's an interesting anecdote about this because Schrödinger spent 2 weeks thinking about it on his winter holidays skiing in Gstaad in Switzerland. And after 2 weeks of skiing, he came up with this equation, which is so famous now. You find it in chemistry, quantum chemistry, Schrödinger equations in physics. But I think it also is a interesting support, gives interesting support to taking time off and going skiing once in a while. Maybe you can discover something like this and get a Nobel Prize to boot. So just almost to finish this this storytelling. So quantum physics has evolved, and I will not spend too much time on this evolution, but we started with wave mechanics, then it was called quantum mechanics after the Solvay conferences, which basically deals with electrons in atoms and electrons in molecules. So that gave birth to what's called quantum chemistry. And basically quantum chemistry, it's all of chemistry because molecules are created from atoms as a result of formation of chemical bonds. So chemical bonds are either sharing electrons or electron densities or clouds again, or donating electrons, which is basically a quantum transitions phenomena. And so all of chemistry is really quantum physics, if you think about it this way. And then the rest of quantum mechanics was applied to larger structures such as superconductors, semiconductors, laser, and all of electronics is based on quantum principles. And we'll talk for a few seconds about it, I think on the next slide, but I just want to say that quantum field theory is a conceptual continuation of quantum mechanics, and that involves interactions with messenger particles, such as you must have heard about the Higgs boson at the very bottom of this edifice, this so-called standard model, which explains all the elementary particles, that involves electroweak unification with weak force electromagnetism and quantum chromodynamics, quarks, gluons, and so on. So quantum physics explains pretty much everything that we know about the universe at the basement level, if you will, except for gravity. We still don't know how to combine gravity with quantum physics. So that's, and then this is the list of these incredible advances that were made possible in our modern world, our technology, due to the application of quantum physics. It's not abstract, maybe the mathematics is, but the applications of quantum physics very, very mundane, but incredibly powerful. Consumer electronics, TV, cell phones, computers, laser scanners, all of spectroscopy, compositional analysis, MRI, NMR, GPS. GPS also uses actually not only quantum principles, but also general theory of relativity. There's a correction for that. Solar batteries, photosensors, photodetectors, PET scans, and all that. So all of it is based on this incredible part of physics. I'll just skip through this quickly. I mentioned two types of particles, fermions and bosons, and they obey different types of rules. Fermions do not like to be in the same state with another fermion, so they exclude other particles. And that's why we actually have atomic states. If electrons were not fermions, you wouldn't have this beautiful organization of atoms into hierarchies where you have the lowest orbit 1s, then 2s, 2p, 3s, 3p, and so on, because electrons are fermions. They can only allow one such particle in one state. So spin allows 2 electrons to be in one orbit or more. Then angular momentum kicks in, but basically spin allows two of these electrons to be in the same state with other characteristics. So one spin up, one spin down. So they are different states. And this is a distribution function of the probability as a function of energy. In the middle, you have the classical function, which is called Maxwell-Boltzmann distribution. At the bottom, you have the Fermi-Dirac for fermions, and the top is Bose-Einstein for bosons. So bosons like to be in the same state, and fermions don't like to be in the same energy state as other fermions. So completely antisocial. Fermions are antisocial. Bosons are social animals, okay, if you will, or party animals. So this is, okay, I will just, we're almost done. I just want to say a few comments about quantum theory of solids. Solids are basically crystal lattices. As you can see here, it's a somewhat distorted lattice for a reason. Why am I talking about this? Because next week we'll come back to it from a different perspective, that of metabolism. So if you think about solids, you seldom think about quantum principles. Let's say a piece of metal or a piece of crystal, but it seems to be pretty well. It's called solid, so it seems to be very steady and rigid. But actually, all the atoms are moving around their positions all the time, just like shown in this cartoon, and they obey actually a quantization principle. And this was obtained, and this was proven by Peter Debye by looking at so-called specific heats. Specific heat is the amount of heat you need to add to an object to raise its temperature by 1 degree. So C is the specific heat, and for crystals or solids in general, it was found that at very low temperatures, the specific heat is proportional to the third power of temperature, T cubed. At high temperatures, it kind of levels off, it becomes constant with this constant R, which is the gas constant. Now, this is one example where Albert Einstein made a mistake or failed to explain something. He tried to explain this property by assuming that all atoms vibrate around their positions independently and use the so-called harmonic oscillator approximation in the quantum sense. And he actually obtained a wrong formula. I'm not quite sure if you see this tab or is it abstracting on my view? You see it?
Yeah.
Oh, I don't know how to remove it. It's in the wrong place. Okay, now it's a bit better maybe. So this formula is incorrect. It actually applies to gases, but not to solids. Okay, now what? Too fast. All right. Debye explained it, and this is important to understand, because remember, Einstein assumed the solid to be a collection of independent vibrating atoms, but you have a lattice, so they are connected by springs. It's like a mattress. Okay, you have coils connected together to form a box spring. Now, Debye assumed that it's different, that instead of independent movement of these atoms, they actually form waves. So these waves propagate, and once you assume that they are collective excitations, then you can explain the whole thing. We'll come back to it next week. Why is this important? Because now this introduces the concept of a phonon, which is a quantum of elastic deformation. It's a wave that propagates through a mechanical system, and it's also something called the collective excitation. So until now, we were kind of discussing individual particles, maybe colliding or maybe overlapping or things like that, forming bonds in chemistry. But when we move to solids and crystals in particular, you suddenly have a new concept, namely a collective of, and that brings us actually closer to biology, because in biology, you don't talk about a single particle, you talk about millions and billions of molecules forming a structure, a protein or an organelle. So it turns out that solids can also be seen as quantum objects, and the signature of a quantum object comes through this specific heat dependence on temperature. It's a bit technical to really understand how it comes about, but it's a manifestation of the quantization of these waves. In other words, these waves need to have nodes on the atoms, cannot be in between atoms. Okay, so you see, this is one of those macroscopic quantum effects. It's important to know that quantum physics applies also to macroscopic, large systems, and crystals and magnets are large. Lasers are large, and they operate on the quantum principle. So now we have lasers, of course, in scanners in the supermarket. You have laser pointers. All of these are quantum devices. So if somebody says quantum doesn't apply to biology because biology is larger than these tiny particles, no, this is wrong. That's not the obstacle. There are some other things. So maybe I will kind of stop around here, just on this provocative thought, and another historical remark. So we'll stop with history today and move on to the present time on Tuesday. But here you see the two famous figures: Schrodinger, representing quantum mechanics, and Darwin, representing biology. And the argument is this: it took us about 350 years or so as a civilization to discover quantum mechanics. Life on this planet has had 2 billion years of parallel experimentation on trillions and trillions of experiments running simultaneously, right? Because every one of us is a bioreactor and some kind of experiment in a living form, and therefore it stands to reason that if it took us only 350 years, life must have found quantum mechanics or quantum phenomena much faster over 2 billion years of evolution. especially viewing this through the lens of natural selection, which amplifies and retains evolutionary achievement. And photosynthesis is one of those early achievements, being able to harness light energy. And on Tuesday, I'll tell you that photosynthesis is a quantum phenomenon. And therefore, it's not a big stretch to think that if plants discovered quantum mechanics, how to efficiently use energy, then other forms, higher forms, must have as well. And the last historical note I want to make here is that the same Schrodinger, Erwin Schrodinger, wrote a beautiful little book in 1944 during the Second World War. He was at that time in Dublin at Trinity College in Ireland. As he wasn't Jewish, by the way, his wife was, so they escaped from Austria. But in that time, he wrote the book called What is Life? And it's actually a book about the first sort of fundamental book about biology seen through the eyes of a physicist. And what are the paradoxical aspects of biological systems from that point of view. I highly recommend it. I think you can read it in one sitting. It's not too complicated, but it is quite profound and still interesting and relevant. So let's see. I will stop here, perhaps, if you don't mind.
Okay, so if you want to unshare, we can try this immersive view.
Should I leave the sharing? Oh yeah, you wanted me to do the stop share. Okay, great.
Yeah. Okay. So let me see. Immersive. Yeah. So. Yeah. Okay, so anyway, it doesn't work perfectly, and in the recording we don't have the names, so the recording is much less revealing, and you can see that the students in the room become very tiny because they're far from the camera. So there's one representation right beside me of the students, but actually in the room. But you can see they're about a tenth the size of the other students.
It's not fair.
But it's an interesting manifestation of physics of a different kind, right? This is Zoom physics, right? So, and it's relatively new. They've had this view only since the end of April 2021. Yeah, but anyway. Okay, any questions? It can come either from the big students on Zoom or the little tiny ones in the room. So all are equally empowered to ask questions. Yeah.
I just had a question about, I guess it was more if I could get some foreshadowing on quantum anesthesiology that you kind of briefly touched upon at the beginning of your presentation. Just thought it was an interesting idea.
Yes, I'll spend a bit more time on it, but I'll tell you what the major thrust of our investigation here is. So, as you probably know, anesthesia is one of the greatest advances in modern, not so modern actually, 150 years old or so, but medicine, and without it, we couldn't do a lot of procedures. But we still don't know how it works. And the reason for it is that anesthetics come in different shapes and sizes, from very small like xenon, a single atom, to small molecules, to very complex organic structures like well, isoflurane or halothane. Some are volatile gases, some are water soluble, but most of them are lipophilic, and the potency of anesthetics is proportional to the lipophilicity. However, there are a lot of lipophilic molecules which are not anesthetic. So lipophilicity, which was postulated as the main properties, doesn't explain what happens. And of course, people think that it's blocking some receptors in neuronal membranes. And apparently, and I'm not an anesthesiologist, but I know a few things about it. Apparently, action potentials still continue traveling due to anesthetic action, but the patient, the person under general anesthesia, doesn't feel anything and doesn't have any memory. So there are several physiological effects, of course, and one of the more recent proposals is that anesthetics actually enter into the cytoskeleton of neurons. So not just membranes, they do bind to receptors, and also membranes themselves change their properties, physical properties. But this new proposal claims that anesthetics bind to the cytoskeleton, which is tubulin and actin, microtubules and actin filaments. And in fact, it has been demonstrated experimentally that all anesthetics bind to a number of proteins, but only two proteins are bound by all anesthetics, namely actin and tubulin. Now, further, it is assumed that, so this brings us to the controllable switching off of consciousness, right? Because during anesthesia, the patient doesn't have any conscious activity, and therefore that is a direct mechanism of affecting consciousness, or turning it off. And the idea is that actually the site of consciousness, and the consciousness itself, is driven by quantum effects. This is beyond a few words, we really have to spend more time discussing it. But the hypothesis that I'm referring to was proposed by last year's Nobel Prize winner Roger Penrose and Stuart Hameroff, who is an anesthesiologist, and they claim that the site of consciousness actually is the microtubules and neurons in the cytoskeleton of neurons, and therefore anesthetics actually turn off this or affect the quantum wave function of these structures temporarily during the procedure. So for, let's say, an hour or whatever, 2 hours, and then they unbind, and then the quantum state of these structures is restored. That's in a nutshell what the hypothesis is saying. With my colleagues at Princeton and Stanford and Florida, actually are exploring this experimentally, and I hope I'll be able to give you a few more pieces of information about it by the end of this course. I hope it kind of addressed your question. I know it's a little bit squishy, but we'll get to it. You'll see some of these ideas in more concrete form.
Okay, so other questions? Either from Zoom or
maybe in the chat box.
Yeah. Yeah, I just put in the chat the general idea that you're not responsible for formulas. You don't have to calculate anything during the exam. You're sort of responsible in these 4 lectures for the really big ideas and the impact on biology and on you as a human being. You know, how
Well,
would it, yeah.
I think this question that was asked by the student just a moment ago, I think this is the biggest idea, in fact, because it strikes at the core of what it means to be human, right?
Sure.
If our consciousness is based on quantum principles, then this is a huge idea, and it has many implications. One of which is that probably it's futile to imagine that artificial intelligence, unless somehow incorporates quantum interactions in it, can replace the human mind. We can replace the human brain maybe, but not the mind. If the quantum principles, we discussed, and I think I would like you to think about these new concepts, which are completely counterintuitive: the lack of determinacy, the uncertainty principle, the superposition and that'll come back later on when we talk about psychology, where our mind can be in two places at the same time. We can have many thoughts at the same time. So some of it actually, when you think about it, it makes sense from the psychology point of view.
Yeah, so, I mean, one way to look at it, at what sentient computers will be able to do, is anything that is formulaic or expressible in words, they'll probably be able to do better than we can. But that is a kind of deterministic statement, right? That's assuming that everything can be only one way, right? But when you have superposition and the possibility of probabilistic activity, I'm not sure that computers will be able to reproduce that. It seems like maybe by its very nature, they will at least have greater difficulty reproducing things like that, things that are probabilistic as opposed to deterministic. So other questions? Yeah, we're four minutes over. I don't know quite where Dr. Tuszynski is, but I think it's a lot later in the day, wherever he is in the world.
Well, I mean, these days, you know how it is. I taught a course in the fall and the winter last year, and I had students from China, Korea, and
Wow.
India, connecting online. And so I'm not that far. I'm actually in Italy.
Yes, that's what I thought. So I mean, there are two reasons not to keep the discussion going on forever, that probably today's speaker doesn't want it to go on forever. But actually, some of the students may actually have other things to do.
And I encourage you to maybe email or prepare questions for the next session, because I'm sure if you think about this, you'll come up with some questions for me, and I'll be happy to address them.
Yeah. So I did find a way that I'm quite proud of sort of making the videos from the course more representative of student activity. So when you go in and watch the videos, when you re-watch areas of it, you get an audience retention peak. And then in the YouTube description, I'm describing what's going on at those peaks. That makes it more likely that people will reinforce your peak. If you came in and rewatched some part of it, then others will also be drawn to that. And it makes the video really intriguing, because it's a kind of accidental representation of what some of the content is, right? If I were to try to describe all of the content, The problem with that is students being busy, then they say, well, I don't need to watch any videos then, because I just look at the table of contents. So this way, that will never be the feature. You'll never be able to sort of figure out what the whole big ideas were in the entire teaching session from these audience retention peaks. But they are sort of idiosyncratic for the people watching the video this term, right? That's where the peaks come from. So yeah. And if you don't like that, but I think you probably will. It's a way for the students to kind of shape the course more and the permanent feature of the course. And you would realize these next 4 lectures are kind of important. Why? Because historically, Jack's lectures get more views than anyone else, right? So in the long term, his fan following will find him, right? And so there'll be lots of other people watching, but when they decide what to watch, it will be the audience retention peaks from the students. It's kind of their starting point, right? So yeah, I think that'll be cool. It's kind of a mixture of his worldwide audience that he's. So there was one year where he talked about computational drug design, and I was so mad because I wanted to talk about quantum biology, but he talked about computational drug design, and so that hasn't ever happened again. But this is what he's teaching you is sort of at the cutting edge of his thought processes, and he does do more practical stuff.
Believe it or not.
Yes. Yeah. So
Well,
okay.
Thank you, Kim. Thank you, the audience, the students, very much.
Thank you, and feel free to send questions before next Tuesday. All right, that's it. Thank you very much, everyone.
See you next week.